Welcome to week 7 of Classical Mechanics 2. Today, we're going to be talking about the Hamiltonian and Hamiltonian mechanics. But before we get there, let's have another think about what we were talking about at the end of last week. We were talking about conserved quantities as they relate to continuous symmetries via Noether's theorem. Imagine I have time as my continuous symmetry. Let's look at my Lagrangian here. I'd like a Lagrangian that does not depend on time. So if I take the total derivative of my Lagrangian with respect to time, I have the sum on I of dl by dqi, dqi by dt, so that's qi dot, plus dl by dqi dot, dqi dot by dt, so this is qi double prime, plus dl by dt. And this term here is 0 since my Lagrangian doesn't depend on time. I also know that my Euler-Lagrange equation says dl by dqi is equal to d by dt, dl by dqi dot. So now we can use this identity to help unpack this term up here. So this tells us that d by dt of pi, this is my conjugate momentum here, is equal to pi dot. dl by dqi is equal to pi dot. And dl by dqi dot is equal to pi. These are the identities we're going to plug in. So that tells me that the derivative of my Lagrangian with respect to time is equal to the sum on I of pi dot qi dot plus pi qi double dot. And if you look at this for long enough, you'll recognize that this is just the chain rule on this term here. So it's d by dt of p dot q dot. That tells us that we can rearrange this whole thing here. We know that this term is equal to 0, so 0 is going to be equal to this term minus this term. So we can pull out the d by dt, and we end up with p dot q dot minus the Lagrangian. And that tells us that everything inside here is equal to a constant. And that is what we call the Hamiltonian. It's the sum on I of pi qi dot minus the Lagrangian. If the Lagrangian does not depend on time, then the Hamiltonian is conserved. So what is this Hamiltonian? If the Lagrangian doesn't depend on time, then the Hamiltonian is just the total energy of the system. To show that, let's consider the coordinate transformation such that we've got Cartesian coordinates, these are r as a function of q, or generalized coordinates q that are a function of r. In Cartesian coordinates, our kinetic energy is merely 1/2 m r dot squared. Ri dot is equal to the sum on j of dri by dqj by dt, so this is qj dot, and r dot squared is equal to the sum on j of dr by dqj, qj dot, times sum on k of dr by dqk times qk dot. To make this a little bit easier to continue writing, I'm just going to call this term here a sub j and this term here b sub k. In terms of my generalized coordinates, my kinetic energy is now 1/2 m, the sum on j and k of aj, bk, qj dot, qk dot. That's my kinetic energy. What about the Hamiltonian coming from our definition? To unpack that, we need to look at pi. We know that pi is equal to dl by dqi dot. And that is equal to dk by dqi dot. And we know that because potential energies don't depend on the velocity a particle takes. This is equal to m times the sum on k of ai, bk, qk dot. If we want to expand the sum on J of Pj, Qj dot, we end up with the sum on J of M times the sum on K of Aj, Bk, Qk dot times Qj dot. And this term here, you'll notice, is exactly twice this term here. This is just twice the kinetic energy of the system. So our Hamiltonian is the sum on I of Pi Qi dot minus the Lagrangian. The sum on Pi Qi dot is just twice the kinetic energy minus the Lagrangian, which is kinetic energy minus the potential energy. This tells us that the Hamiltonian is just our total energy. Let's compare and contrast Lagrange's method and Hamilton's method. The definition of our Lagrangian, depending on the coordinates q, q dot, and t, is just the kinetic energy minus the potential energy. And here we have the Hamiltonian, which depends on a generalized coordinate q and pi. And these pi's are equal to dl by dqi dot, and these are called the conjugate momenta. In Lagrange's method, q and q dot define what we call a configuration space. And any point q, q dot in that space defines the state of a system. So that's its position and velocity. And that's something that you'll have at every point along the trajectory. It'll be some combination of q and q dot. This combination of q, q dot is called a state space. Lagrange's equations give a path through state space that's called an orbit. Hamilton's method is a little bit different. In Hamilton's method, we have a combination of Q and P. This defines a phase space. You may have heard about this when you've taken quantum mechanics and other classes. Hamilton's equations give trajectories in phase space. They evolve positions and momenta simultaneously. And next week, we're going to be talking a lot about phase space and how we can understand dynamics of the systems based on trajectories through phase space.